Good morning, everyone. My name is Alessandro Corsi, and I am a PhD student at Laval University in Quebec, Canada. And today I'm gonna talk about my research work with the title Two-Channel Data Transmission on a Polarization Maintaining Highly Elliptical Core Fiber without MIMO. For the outline of this presentation, I will start talking about some fiber works on mode division multiplexing in a MIMO-free condition. Then I will discuss a novel few mode fiber that we proposed with the name highly elliptical core fiber. And then I will jump to the experimental results for the data transmission over this fiber. And finally, the conclusion. So mode division multiplexing can be realized with mode groups. And here are listed some examples that reach MIMO-free transmissions. And they, in particular, they are composed by an elliptical core shape, and they reach a different number of channels, so respectively 2, 3, and 4 channels. Mode division multiplexing can have place also over vector modes. And so an example can be orbital angular momentum modes. So here the authors used an air core fiber to reach 12 channels. Instead, the second fiber was proposed by our group a few years ago. And it is an elliptical ring core fiber supporting 6 vector modes. And we demonstrated the transmission over those modes. And the fiber was also polarization maintaining. So the objective of our work is to propose a novel few mode fiber having polarization maintaining properties, more channels, high modal birefringence, and reach MIMO-free data transmission over orthogonal modes for short links. To give some details and benefits of our fiber, it supports 5 spatial modes with 2 polarizations for a total of 10 vector modes. It is compatible with standard fabrication techniques. The modes are linearly polarized, so this simplifies the max and the max. The refractive index difference between core cladding is low, so this simplifies the fabrication and decrease the loss. And then the effective index difference between the spatial modes and the effective index difference between the polarization modes is higher than previous fibers. And then the last benefit is coming from the scalability of our fiber. So here we can see the fiber design, which is composed of a high elliptical core, which gives the name to the fiber. And we have also a depressed index trench to reduce the bending loss. In the figure, we can see the comparison between the design and fabricated fiber and the refractive index difference. And in the table, we can see instead the geometric parameters. So we can observe that from the design and fabrication, the parameters were very close. And I want to mention that all the results about the design of this fiber can be found in the paper listed below. So now let's talk about the main benefit coming from this fiber, which is the thermal stress. So when we work with circular core fibers, we have that during the fabrication, the stress is applied evenly around the core. So we do not have birefringence for those fibers. When working instead with highly elliptical core, this stress is applied in an asymmetric way along both core axes. And this strongly impacts the birefringence. So this thermal stress, together with the highly elliptical shape that we know that it improves the birefringence, give us effective index difference values higher than 10 to the power of minus 4. So here we can see the modes of our fiber, the modes supported by our fiber from design to fabrication, and the modes look like lobes distributed on one-dimensional array. And from the two, they look very similar. Now let's talk about the effective index difference for our fiber, and we measured in the lab with a fiber grading technique. So what we did is we excited one mode at a time, and we measured the transmission spectrum, and the peaks wavelength give us the information to measure the effective index difference between the mode. And then what we did is to simulate this fiber with including the thermal stress analysis. And what we found is that there is a good matching between simulation and experiment. And then what we did was also to measure, to simulate the fiber without the thermal stress analysis. And what we found is that the fiber didn't show polarization maintaining properties. So there was no matching between simulation and experiment. So this is why we need to consider the thermal stress analysis in our simulation. I want to mention that those results can be found in the paper listed below that was accepted for optics letters, and it will be available online soon. So what we did, we characterized also the fiber by measuring the linear polarization properties. So we measure polarization extinction ratio, and then we define the mode stability. So by measuring the power fluctuations. So for the PER, what we did, we excite one mode at a time inside a 5-meter sample of our fiber, and by turning off 90 degrees the polarizer, we were able to measure the maximum and minimum power, and we found values for the PER higher than 24 dB. So this means that the fiber modes have good properties for linear polarization. And then for power fluctuations, we turned the fiber around a 30-millimeter radius rod. We fixed the polarizer, and then we measured the powers after 5 turns. And we found values for power fluctuation lower than 0.24 dB. So this means that the modes were quite stable. And again, those results can be found in the paper below. Now let's talk about the experimental setup we used for data transmission. So we generated our QPSK signal, and then we split into branches, channel A and B. And then we use an SLM, programmable SLM, to generate in free space the highly elliptical core fiber modes. And in particular, what we did, we excite both polarization of the same special mode to combine in a 1 kilometer spool of our fiber by using a 6-axis stage for fine tuning and fine alignment. And then at the output, we use another SLM to convert back the modes to a Gaussian shape to couple into a single mode fiber going to our coherent receiver. The results, we measure bit error rate versus OSNR at 24 gigabaud. Solid lines represent the case of single polarization, and we can see that the curves follow the theoretical curve. And then the marked lines represent the case when we excited 2 polarizations. So we found that the fiber crosstalk imposes an OSNR penalty between 2.3 and 3.5 dB at the effect threshold. Then we measure bit error rate versus baud rate at fixed OSNR of 24 dB. And here we found that the bit error rate is below the effect threshold, even at that baud rate up to 32 gigabaud. To conclude my presentation, what we did, we demonstrated a MIMO-free data transmission over 2 orthogonal polarizations of all special modes supported by the fiber. And this was allowed by a sufficiently large model birefringence showed by the fiber. And then we also demonstrated MIMO-free data transmission for baud rates up to 32 gigabaud. So I want to thank our partners, so Natural Sciences and Engineering Research Council of Canada and Huawei Canada. So thank you for your attention, and here you can find my email. So if you have any questions or comments, please write to this email. And have a good day, have a good conference, and see you. Thank you for your attention.